Welcome to the Network Plus Prepcast, your dedicated audio companion for mastering every objective on the CompTIA Network Plus certification exam. This series is produced by baremetalcyber.com. The Internet Protocol exists in two major versions, IPv4 and IPv6, each of which defines how devices are identified and addressed across networks. IPv4 has been the foundation of network communication since the early days of the Internet, while IPv6 was introduced to overcome the limitations of its predecessor. These two protocols differ not only in length and format, but also in how they handle packet transmission, address configuration, routing, and scalability. Understanding these differences is critical both for designing and supporting modern networks and for success on the Network Plus exam. Comparing IPv4 and IPv6 is more than just recognizing that one has longer addresses. Their structural differences impact how networks are planned, how devices communicate, and how traffic is secured and managed. The transition from IPv4 to IPv6 is ongoing, and many networks must accommodate both protocols simultaneously. This dual support environment adds complexity, but also flexibility, allowing organizations to move toward IPv6 adoption without disrupting existing services. On the Network Plus exam, you will frequently be asked to distinguish between IPv4 and IPv6 structures, recognize valid addresses, and apply version-specific configuration methods. IPv4 addresses are written in a 32-bit binary format and are most commonly represented using dotted decimal notation. Each address consists of 4 octets, separated by periods. Each octet ranges from 0 to 255, corresponding to the possible values of an 8-bit binary number. This structure limits the number of possible IPv4 addresses to approximately 4.3 billion, which was sufficient during the early days of the Internet, but has proven inadequate in the era of mobile devices, IoT, and global connectivity. IPv6, on the other hand, uses a 128-bit binary format, vastly expanding the number of available addresses. IPv6 addresses are written in hexadecimal and are separated by colons instead of periods. An IPv6 address consists of 8 groups of 4 hexadecimal digits. This structure provides a staggering address space enough to assign unique addresses to every grain of sand on Earth many times over. This capacity ensures that address shortages are no longer a concern and that the Internet can scale indefinitely. One of the most immediate differences between IPv4 and IPv6 is how addresses are notated. IPv4 addresses are expressed in decimal form with values that are easy to read and calculate for network segments and subnets. IPv6 uses hexadecimal notation, which can appear more complex but is better suited to expressing 128-bit values. IPv6 notation includes rules for abbreviation. For instance, leading zeros within a block can be omitted, and contiguous blocks of 0 values can be replaced by a double colon, but only once per address. The header format of each protocol also highlights fundamental differences in design philosophy. The IPv4 header is variable in length and includes fields for fragmentation, checksums, and options. While this provides flexibility, it adds processing overhead and complexity for routers. In contrast, the IPv6 header is fixed in size and simplified, removing many legacy fields and relocating optional features to extension headers. This design makes IPv6 more efficient for modern high-speed routing and easier to process in hardware-based devices. Fragmentation is another area where IPv4 and IPv6 diverge. In IPv4, any router along the path can fragment packets that exceed the maximum transmission unit, MTU, of the next hop. This can create inefficiencies and increase reassembly workload for the receiving device. In IPv6, only the sending host is permitted to fragment packets. Routers do not perform fragmentation. Instead, the sending host uses the path MTU discovery process to determine the smallest MTU along the route and adjust packet sizes accordingly. If fragmentation is needed, IPv6 uses dedicated extension headers that signal the receiver to reassemble fragments. IPv4 relies heavily on broadcast for various network functions, including address resolution and service discovery, broadcast traffic is sent to all hosts on a subnet, which can create congestion and security issues. IPv6 eliminates broadcast entirely. Instead, it uses multicast for most functions that would have used broadcast in IPv4. For example, IPv6 uses the Neighbor Discovery Protocol, NDP, over multicast to find routers and resolve addresses, and it uses anycast to send packets to the nearest instance of a service. This makes IPv6 traffic more efficient and better suited for high-density networks. Address assignment methods also differ. IPv4 devices typically obtain addresses through manual configuration or via a dynamic host configuration protocol, DHCP server. These methods require administrative oversight and infrastructure. IPv6 offers additional flexibility through stateless addressed autoconfiguration, SLAAC, where devices automatically generate their own addresses using a combination of router-advertised prefixes and locally determined identifiers. IPv6 can also use DHCPv6 for more managed environments, offering a combination of self-configuration and administrative control. NAT usage further distinguishes the two protocols. IPv4 networks rely extensively on network address translation to conserve address space and provide security through obscured addressing. Most home and business networks operate behind NAT-enabled routers. IPv6, with its abundant address space, does not require NAT. Each device can have a globally unique IP, supporting true end-to-end communication. This restores a fundamental principle of the Internet, direct device-to-device communication without intermediary address translation, simplifying some aspects of networking while introducing new security considerations. For more cyber content and books, please check out cyberauthor.me. Also, there are other podcasts on cybersecurity and more at baremetalscyber.com. Security capabilities are a major distinction between IPv4 and IPv6. While both protocols support IPsec, which is a suite of protocols used to secure network communication through encryption and authentication, the way they implement it differs. In IPv4, IPsec is optional and must be configured manually, often relying on third-party tools or overlay. In IPv6, support for IPsec is built into the protocol specification itself, making it a standard feature of all IPv6 implementations. This design encourages widespread encryption and secure traffic by default, although in practice, security still depends on proper configuration and policy enforcement. IPv6 introduces new address types that replace and expand upon those used in IPv4. In IPv4, addresses are either unicast, broadcast, or multicast. In IPv6, the broadcast function is eliminated and three primary address types are used: unicast, multicast. Unicast addresses are assigned to individual devices. Multicast addresses are used to send data to multiple devices simultaneously, and anycast addresses allow data to be routed to the nearest of multiple possible destinations, based on routing metrics. This structure supports more efficient delivery of services such as content distribution or routing protocol updates. During the global transition from IPv4 to IPv6, many networks are deployed in a dual-stack configuration. In a dual-stack network, devices and infrastructure components are configured with both IPv4 and IPv6 addresses, allowing them to communicate over either protocol. This is the most compatible approach to transitioning, as it enables communication with legacy IPv4-only devices and newer IPv6-only systems simultaneously. Dual-stack deployment is common in enterprise networks, data centers, and service provider environments, where uptime and interoperability are critical. To ease the migration between IPv4 and IPv6, several transition techniques have been developed. These include tunneling methods like 6-to-4 and Teredo, which encapsulate IPv6 traffic inside IPv4 packets to traverse IPv4-only infrastructure. Another approach is NAT64, which enables IPv6-only clients to communicate with IPv4-only servers using protocol translation. These techniques provide compatibility during the migration period and help maintain network continuity as organizations gradually adopt IPv6 without needing to immediately replace all equipment or software. Device compatibility is an important consideration during the IPv6 transition. Most modern operating systems and network hardware support both IPv4 and IPv6, but older devices may not have the necessary firmware or software updates. In these cases, upgrades or replacements may be required to fully implement IPv6. Network administrators need to assess the IPv6 readiness of routers, switches, firewalls, and end-user devices before deploying IPv6 broadly. Compatibility planning ensures a smooth rollout and avoids unexpected service interruptions. Routing behavior is also more streamlined in IPv6. The large address space and hierarchical structure of IPv6 addresses simplify route aggregation and reduce the size of routing tables. IPv6 is designed with global routing efficiency in mind, using aggregation-friendly address assignment by ISPs and organizations. This structure minimizes the need for route summarization or policy-based routing, resulting in faster convergence and easier scalability. Without NAT in the path, IPv6 packets follow more predictable paths, improving performance and simplifying troubleshooting. Both IPv4 and IPv6 have loopback and reserved addresses, but they are expressed differently. In IPv4, the loopback address is 127.0.0.1, and the entire 127.0.0.0/8 range is reserved for loopback purposes. In IPv6, the loopback address is ::1, a shorthand for an address with all bits set to 0 except for the last. This address functions the same as in IPv4, allowing a device to test its own TCP/IP stack. Both protocols include additional reserved ranges for testing, documentation, and special functions. Recognizing these ranges is essential for configuration, diagnostics, and exam preparation. On the Network Plus exam, expect to see questions comparing the structural elements of IPv4 and IPv6. You may be asked to identify an IPv6 address by its format or recognize the absence of broadcast in IPv6. Questions may also test your ability to choose the correct addressing method, such as SLAAC versus DHC, or to interpret routing behavior and transition method. Memorizing key characteristics such as header formats, address lengths, and notation rules will help you quickly and accurately respond to exam items focused on protocol versions. You may also encounter configuration-based questions. These could involve determining why a device can't communicate over IPv6 in a dual-stack environment, diagnosing prefix assignment problems, or interpreting a given IPv6 address to identify its type, such as link local, global, unicast, or multicast. You'll need to be able to recognize structural patterns, interpret hexadecimal notation, and understand the role of each part of an IPv6 address. Understanding IPv6 addressing logic not only helps on the exam, but also in practical network design and management. In conclusion, IPv4 and IPv6 represent two generations of the Internet Protocol, each with distinct structural, functional, and operational characteristics. IPv4 has served the world for decades, but faces limitations in address space and routing efficiency. IPv6 addresses these limitations with a massive address pool, simplified headers, built-in security features, and better support for automation and global communication. Both protocols are still in use, and understanding how they differ and how they interact is essential for network professionals and anyone preparing for the Network Plus certification. Thank you for listening to this episode of the Network Plus Prepcast, your trusted audio guide to the CompTIA Network Plus certification. This episode was produced by baremetalcyber.com. For more cybersecurity podcasts, books, and resources, visit baremetalcyber.com. Thanks for joining us for this episode of the Bare Metal Cybersecurity Plus podcast. For more episodes, tools, and study support, visit us at baremetalcyber.com. And before you take the test, make sure to check out the practice questions in the book Achieve CompTIA Security Plus SY0-701 Exam Success by Dr. Jason Edwards. They cover every domain and are a powerful way to lock in your knowledge.